reading. What time is it? 3. Sometime. Okay, so last class we worked on PID controller. We explored 2 different ways of tuning PID control coefficients, manual and using MATLAB toolbox. At the end of the day, in both case scenarios, you have to include yourself in the loop as engineers to decide what values for KP, KI, and KD you would consider. Now, so PID control is one method of designing controller. All right, so 3-parameter controller. I think I was talking to one of the students after class, and I thought about an example. I think it's good if we talk about that here. So what does it mean to tune a controller? And we discussed a lot about, you can't just go, okay, on the paper it looks good, KP, KI, KD. The response looks good, I'm gonna get those numbers and then go with it. I told you it has some implication on the physical aspect of your project and the system, right? So think about, you're designing a cruise control, all right? And you want to go from 0 to 60, and you wanna go as fast as possible. You'll design the controller to go 0 to 60 in 4 seconds. Everything looks good. All right, you're giving this to me. I drive a Jeep. 0 to 60 in 4 seconds is not possible, right? Why? Kevin? The engine cannot accelerate as fast, right? So that's the time, the rise time. So you're expecting my engine to rise, to settle, that's the settling time, to settle in 4 seconds, 60 miles per hour, while my engine can't handle that. It just simply does not happen. So it doesn't matter how good or how fast your controller is, depending on your system, your controller cannot compensate for your system as much. It can do a little, but at the end of it, it comes to the engine of the car. Now, if you're driving a Ferrari, that's a different scenario. I don't know what's the number 0 to 60 in Ferrari, it was definitely better than Jeep, right? So you cannot change your system. So your controller is at the most as good as your system, okay? So when you are tuning, when we say that, hey, this number, does it make sense? Does 0.001 second rise time make sense for the system? That's something that as engineer, you need to decide. Maybe you need more information from the project, okay? So it's not all on the controller side. Okay, I usually encourage my student to always check the answers they have and ask, does this make sense in real life? Okay, or does this answer make sense at all? If it didn't, if it's an exam, you got an answer that doesn't make sense, write to me. I have this, it doesn't make sense, don't know what to do. I've had that in exam 1. And I give you the point because you're smart enough, you know, this doesn't make sense. You went wrong somewhere, you can't find it, but you know, this shouldn't be like that. So to me, that's as good as you calculated the right number. Now, don't go and calculate something and say, don't check. I'm just gonna say this doesn't make sense. I expect you to be able to find the error. But if you couldn't, at least you can tell me, I also don't think so. Don't think is a good answer. All right. So another method of designing a controller, if you remember, we talked about it, is pole placement. Okay, what does it mean? Pole placement is a method of designing a controller. What does it mean to place a pole? What are you changing in your system? Well, when I say system, closed loop, because your system, as we said, you can't change. The motor is the motor. The control is what you're adding to your system. Now, when we say pole placement, what do we, or when I say pole placement, what do I mean by that?
In place your poles either closer to the imaginary axis you want, desires more further away.
Okay, so first, a couple of good things. When we say pole placement, first of all, what domain we are talking about where we are? S domain, right? So when we say pole placement, what Jesse just said, it was this, right? Real axis and imagine, well, the other way around. Real, oh my God, imaginary axis and real axis, and then place a pole here or here, right? then it shows the performance of your control. But put a pole on the stable side somewhere, and then look at the response and see how it changed, right? Now, when we say that place a pole, how do we actually do it using a controller? Now, I know I need to put a pole at -2. That's -2. How do I actually do it? Any idea? Something has to change in the transfer function. Now, something has to change since we are designing a feedback controller. It's a closed loop, right? Something has to happen in the closed loop transfer function of the system. So whatever your block diagram looks like, you have to get you have to reduce it to final transfer function. Then you have to look at the denominator, right? That's where we get the pole. And then we have to figure out, okay, what do we need to change to either move one of the poles of the system, right? Or place a pole in the system. We learned that if we add an integrator to a system, we are placing a pole at 0, right? 1/s, right? So we have a good method that can tell us. Now, let's say that, okay, I want to place a pole. I don't exactly know where to put it. I don't know if it's -2. I just know I need to put a pole in the denominator, like change the denominator such a way that there's a pole, but I want my system to be stable, but I actually don't know where it is. So there is a method that can tell you at least where, around what neighborhood you can place a pole that could be close to what you want. All right, we're gonna review that today. So I'm assume G is a closed loop transfer function of a system. We don't know what the system is. We have the transfer function. Now, if you see in the denominator, that's where we get the pole, right? We put the denominator equal to 0. Now, I have a K value here. So I don't know where all the poles are, right? The poles depend on K. Now, let's plot all the poles starting K from 0. When K is 0, there's nothing there, right? So K from 0, draw the pole, and then K1, K2, K3, K4. This is K5. When I say 5, like the 5th number that I go from 0. So what do you see here? You see a pattern. As the pole you're increasing in this example, if you connect all of these, they are going to connect, right? So you don't exactly know how this connects, but let's say that this is like a fork. All right, for now, just to connect it, you could just, we will talk about how to do that. But if you give enough Ks, it would actually draw that shape for you. So increasing K from 0 to infinity, let's say infinity here, puts the poles of the transfer function, takes them from the left and moves them to the right, cross the imaginary line and goes to the other side. Now, what do you think about this pole, this pair? Are they favorable? No, because it makes our system unstable, right? So whatever we are increasing the K, we have to stop somewhere. Where is that somewhere? Exactly, because this is marginally stable, right? So first of all, you will increase K from 0 to until you get to that line, because behind that, the system is unstable. So designing a control is to make the system stable. So simply just looking at how it changes, it will give us some information. Now still we have so much else to cover that where to actually put the poles. If you remember your homework, question 1, you had 2 different systems, right? Am I correct? That's the one, right? G1, G2, I asked you to plot the poles and then plot the responses and tell me what do you see. Now, one of the system was first order, the other one was second order and third order, or fourth order? Fourth order. So 2 very different systems. But then when you look at the responses were very close. They had the same shape. There was a little bit of offset between the 2, right? So now that offset is because of the DC gain, the number like 550 on top. So in my solution, I showed you another same fourth order system with a different DC gain, and the response was very close to the second order system. Do you remember? Do you check the solution of the homework before exam? Do that. So homework questions are designed for, like, I designed them with a purpose. So to teach you little things while you're doing it, so you get, okay, it makes sense. Because if I tell you, it wouldn't have that effect. So why the two systems that are two order of magnitude different, that have two order of magnitude difference from each other, why do they have similar response? The other one has more poles, right? Yes. So by that, it means that the poles that were closer to the imaginary axes, they were the same. The different pole in the from the fourth order system was 10 times over, so like 6 to 10 times over the dominant pole. It does not have much effect. So there's a slight difference. So it is important where to put the pole. So I made a second order system, fourth order. I placed pole because I thought, okay, this is going to help to stabilize the system, but I put the poles too far from the existing poles, the dominant poles, right? And then it didn't have any effect. So simply adding poles to a system does not fix the problem. You need to know where to put them, and it depends on where the current poles are. So if you have poles closer to imaginary line, it's basically when you add a controller, you're pushing the system towards, like, those dominant poles are like a magnet. They just grab the whole system toward themselves. So if you wanted to change that, if I wanted to change that, instead of putting the new poles 10 times over, I should have put them maybe 2 or 3 times to the left side. So it grabs the system to the left. Okay. But how do I know, like, all of this? If we look at the root locus of a system, it would tell us. So today we're going to go over what root locus is and how it can help us to know where to put the pole. All right. So, and the reason we're doing it is that, well, we have a design problem. We need to design a controller, right? We don't know where to put the pole that we get that stability that we want. All right. So, and we know that when we add something to our system, we need to make sure the system is not too sensitive to it, so it doesn't backfire. Basically putting a pole on the right side or pushing the system to the right side. I'm going to, like, so this is an example of how the poles can impact. So I've changed the K from 0.1 to 9, 10, 20. Doesn't have to be in order. So different value from 0 to infinity, I'm going to draw the pole, and you see that for the same system where the new poles will land. Now, have we talked about characteristic equation before I go there? Yes. So if you have a closed loop transfer function, the denominator, the equation of the denominator is going to be your characteristic equation. That's where you get the pole from. So if I say that for a transfer function with characteristic equation of this, you don't have any information about the zeros of the system, right? I just gave you the denominator of the closed loop transfer function. So this has the controller in it. You don't know what the actual system is. You can separate it, but from this, you need to do a little bit work to find out what is the actual poles of the system, what are the poles because of the system. But at this point, we don't care. We want to see the impact of our controller. Now for K 0.1, my pole is going to be at negative 5.8. So here and negative 2. And then at 2, so basically I put here 0, I put here 2. So I'm changing my equation, right? That's why the poles are going to be different. So this is s squared plus 6s equal to 0. That's why the poles change, because I'm changing my equation. So that's for that. And then negative 564, so close to here, negative 35, close to here, then negative 3 and negative 3, those two are on top of each other, negative 3 plus and minus j, then negative 3 point there. So changing K is giving us different poles. We always are trying basically to find that pattern because I didn't find all the points in between. It just takes so much time. If you plot for all K's, it's going to be something like that. So this is your root locus. Root locus traces the position of all the poles. If you increase K from 0 to infinity. So now I started from 0, so I know my starting point, right? And then as I increase, it's going toward -3 plus minus 3.3J, right? So there is a direction to it. So it went this way. And this one went that way. Okay. Yes. So K equal to 10 is -3 plus J and minus J. Did not plot that.
I think it was just that.
This one?
Yeah.
What is the problem?
I think you have the X on there.
Oh, yeah, like here. Yeah, I didn't have it here. Thank you. Even better. Yes. So it has to cross all the poles, right? There shouldn't be any pole that the locking does not cross. Thank you. So this purple line is called locking, right? So root locus is the trace of all the roots of the closed loop transfer function, and the lock is the trace of all of them. Now, if you have free time on your hand, put K equal to 0, 1, 2, 3, 4, 5 until 20. It's going to produce poles that exactly are tracing this line. I'll promise you. All right. So instead of that, we are going to find ways to draw this locking. And then we know where the poles are going to be. Now, drawing this locking, you don't actually need to know where all the poles exactly are going to be. There are some rules. If we follow them, we can easily draw these. So it's kind of like a game, like estimation. What is the angle? Where do they start? Where do they finish? And then with what angle they're going to leave, with what angle they're going to arrive to those poles at infinity, and then you kind of guess. It should look like this. That's enough. That's really good. Then you will say that, okay, I'm going to put my pole here. Then you pick a pole with that value, calculate, look at the response, and say, ah, this looks really good. That's what I wanted. Or I need to change a little, but you still have your focus, right? You go back and see what's the next one that I want to press. So creating educated guess result, and then pick your controller from that. Only the places that the pole will place will be on them. And then now, if you needed to place a pole near imaginary axes, you know that you have to choose something like the controller, your pole somewhere here, right? Then it will help the system to be stable. Does this table and this lock key make sense to you? That what's the point of having root locus? So we already talked about this item, which is root locus is the path of all the roots. If you change K from 0 to infinity in the closed loop transfer function, right? The characteristic equation, that's really important. Now, okay, before I go there, I put an example here for like self-study if you want the case study. But this example, I looked at it again. The system is represented in, is not in transfer function. In, say the space representation, but it's a system, it doesn't matter. So you start from say the space representation and then go to transfer. All right, so when you start, don't get confused. Oh, this is in time domain. It is representing time domain. You have to bring it back to frequency domain, S domain, and then start with locus. All right. if you wanted to do, this is extra stuff, but I'm not gonna go over it unless you have questions, then we can discuss in office hours. All right, so now let's look and see how that K, that was our controller, appeared in the denominator of our closed loop system, right? So think of a system GS, and you're adding a controller K behind it. So K could be a KP, right? Because K is just a gain, a value, it doesn't have anything else in it. Now, if you write the closed loop transfer function of this, you're gonna get kg over 1 plus kg, right? So the first two are in series, you multiply them, then get the feedback, kg over 1 plus kg. That's the closed loop transfer function. Now, if you look at the denominator, which is the characteristic equation, it has k in it. That's why k appears in the denominator of the closed loop. That's why we did the closed loop. So from here, whatever we decide for k, that's actually on controller. This k, if you change it from 0 to infinity, is your root locus, right? Basically, all the possible poles of this system are going to appear in your root locus. So you can give a k that is meaningful, or you would know all the k values. You just have to pick what pole I want to place, go read the k, and then choose that k, right? So usually, like when I give you an example, I either will give you the characteristic equation, or I will give you something like this, which is a characteristic equation, but in terms of 1 plus kgs. So the controller is behind the GS, so you can easily identify what it is. But if we say that GS is QS over PS, just some numerator denominator inside the denominator, okay? So we picked the denominator, we forgot the actual system, and we are saying that, okay, that GS is gonna have a numerator denominator. And if we call it PS and QS, we can write this, we can open this up. And sometimes we can write it as this also is true. So sometimes I might give you the one on the right. I might give you this. So some term of S plus K times some other term of S. You always want to make it look like this basic form, because then easily you can say what your K is. All right. Does that make sense? So these two can go back and forth. They are both the same thing. I might give you 1 plus K times something, or I might give you that sentence. They're both the same thing. Do I have an example there? No, there's an example on the next page. All right. Okay. So I'm gonna draw a block diagram for you here. 1 over S plus 1, S plus S minus 1, negative 1. Okay. So if I don't know if you can see or not, there are 2 poles here, right? So your system, your plant, let's call it plant, has 2 poles, correct? Your original plant, -1 and +1. So one of them on negative, what is it? -2. So this is 2. Nope, the other one is 3. So as this is S called 2, S -1. All right, so this system, just the plant itself. So for the plant, so if we draw S domain for the plant, we have 2, +2, and -1, correct? That's the plan. The two poles of the plan. Is the plan stable or unstable? Unstable. Why? It has the pole in the right half plane, right? Now, if I need to design a controller to fix this problem, right? One way is to drag this pole to the left side. That's why we can place the pole on where we actually want. So you're changing the pole of the system, moving it to the left. That's our one way is that, right? You could just design a PID controller, fix it differently. You could also grab this pole to the left. Now, how do I do that? If we say that there's going to be a K controller behind this plant, if we write the closed loop transfer function and then plot the root locus for it, we see that there are traces in this that are only on the left-hand side, correct? So if the pole was there, the system would be stable. Let's say the new pole, I'm going to show with red. If the new pole was here, this is your 0 line, okay? If the new pole was at S equal to, for example, -5, would that fix the problem? Both pole on the right-hand side, on the left-hand side? Yes. So I know this is root locus, right? For every pole, there is a corresponding K. So if I know what that K is, and I assign that as the controller, the closed loop system's pole would be -1 and -0.5. Then my system is stable.
Could you also edit the so you could place?
That's different. Yes. So you're trying, so designing controller is finding a strategy to fix a problem, right? So you could, usually you don't choose a 0 because if there is a noise from the environment, and then that will place the 0 slightly, like move the place of the 0, then your system is unstable. So that whole, like, we talked about it in the lecture, one of the lectures, which zeros are, we can do that. You find the dominant pole and then put a 0 next to it. You don't cancel it, you put it next to it, so it will change the behavior of the system. Okay. If you do that and drop root locus, you will see that all the locus are going to change. But this is the method that we change the location of the pole. All right, so there are different methods of designing a controller. PID, which is the 3 term, placing pole. There is designing compensator in the frequency domain. You can choose place a 0, but only near the dominant pole. Okay. Right now, we want to use root locus to place the pole of the system in a stable region. Okay, so let's focus on that. Now, root locus tells me, hey, if you have a controller, you change the value from 0 to infinity, that K is the controller. The pole of this system, so this was the original pole, right? So it looks like it started here, it went up, and this one went down because of the different color it showed me, right? So this is for all the K, these are all the poles. Now, if I want this system to be stable, if I choose the poles on this side, any of the K that created a pole on the left side, I fixed this stability problem on my system, right? We're only for now talking about the stability problem. Now, the system is unstable. Okay, then we have to go next and check other specification, correct? Agreed? The first problem is always make it stable. Make sure all the poles are on the left-hand side. So using root locus, we can decide on a K, which is a gain, which is like a KP gain, right? Proportional, and fixed on the stability problem. So that's one way. A lot of time, from there, you can play a little bit to actually satisfy the rest of the requirement too. But for now, the big problem is, hey, let's make this stable. Now, the dilemma for this class is we can draw by hand. Excruciating. We can just stop it. Pretty easy. All right. The thing is, if we use the software without understanding how this happened, we won't get that intuition to where to choose K. like why that K is changing the system such and such. All right. So for that matter, to just help you understand this better. So when you look at the root locus draw by the software, you understand what happened, why there are different color lines, because there was 2 different colors and it's really important, the colors here, and why they behaved like that. We need to go over drawing by hand. Okay. So your book has a whole chapter 7, how to do this. I used to teach it exactly like that, like 2 weeks of let's draw this, because I wanted to make sure that you understand. But then if you're designing anything, you're going to just plot using MATLAB. The plan, the new plan this semester is, I will tell you the rules. We would do a couple of light examples. All right. Once I know you understood, we just use the software. But you have to show me you understood. Otherwise, I'll put you through 2 weeks of drawing by hand. And it's not fun because there's so much into it. Okay. So I'm going to start. So I want everyone to be awake. So take 2 minutes to wake yourself up. You took your shoes off, like you fall asleep. That makes you uncomfortable. Shoes make us uncomfortable. That's why we say it.
I'm up.
You're up? Okay. You know, I call your name if you're sleeping. I'm not worried that you're gonna do that. That's fine. Very good.
I saw the email.
Yes. All right, you're all awake. Let's get this started. Exciting stuff. All right. So, great start. Root locus procedure. You always want to start from the basic form. All right, because we want to get that P over Q over P. Great, two mistakes for 30 seconds. We are going to use those two, numerator and denominator, to plot the root locus. Now, again, we already calculated the closed loop of our system, right? So this characteristic equation comes from the denominator, the actual transfer function. Don't forget that. Now, always put it in the basic form. What if it was not in the basic form? What do we do? You remember there was the left side and right side. So what if we had all the PQs? What do we do there? So first of all, this is your closed loop transfer function. We grab the denominator, S3 cubed 4s squared plus ks plus 1. How do I fix this? Equal to 0. I'm going to put all the items and terms that don't have k on one next to each other, all the one that have k after that. So I'm gonna write s squared plus 4s cubed plus s squared plus 1 plus ks equal to 0. Now you can tell what to do, right? To make it 1 plus k cubed. I'm gonna divide it by these terms, non-k terms. So if I divide by this would be 1 plus ks over s cubed 4s squared plus 1 equal to 0. This is that g of s. Now I know my qs is going to be s, my ps is going to be, I need it to be this form because I need that P and Q term sentences. All right, that would help us to draw our root locus. So a lot of time, I will give you the characteristic equation. You just have to do that. Sometime I will give you 1 plus kg. So remember that it always have to be in 1 plus kg form. All right. Easy, right? So step 1, pretty easy. Step 0, actually, that's a step 0. So there are 8 rules. Your book says 7. I separated it. I made it 8. So it's just a lot easier to separate things. Rule number 1 is that there are going to be n line or log key when n is the degree of p or q, whichever is greater. So in our previous example, this is s to the power of 1, right? This is, so the highest here is 1, the highest here is 3, right? So that's a degree. Which one is higher? 3. I'm gonna expect 3 of those lines. So there will be 3 colors. All right. So I'm just gonna write power of s. So you love this. Okay, that's rule number 1. You need to know how many lines are gonna be there. Then as k increases from 0 to infinity, which is the root locus procedure, the roots moves from the poles of the GS to the zeros of the GS. So do you remember I said there's a direction, that direction is important. So GS is what we just created here, right? So how do I find the zeros of this transfer function? Put the numerator equal to 0, and then the poles is put the denominator equal to 0. Well, first of all, there are just 1, 0, and 3 poles. let's say. There is a reason for it, and we're gonna fix that. We're gonna deal with it. But it is important to know that you always, the lock key always goes from zero to from a pole to a zero. From a pole to a zero. Now, let's just work on an example, all right? If I only have one pole, if number of pole is 1. Number of 0 is 1. So let's say there is a 0 and there is a pole. Okay. First of all, if the system has 1 pole and 1 0, how many lock key the system has? 1. They're both equal, right? So I would expect 1 line only, right? That line goes from the pole to the 0. Here, pretty simple. That's the root locus. And you put the direction so you know. It's going from the pole to the 0. Cool. That could be a system, and that's the root locus. Pretty stable, everything looks good. Boring, right? Now, what if the number of pole and zeros are not the same? What do we do? Let's say there was a pole here, there was a 0 here, there was a pole here, and then whoop, there's no 0 over there. So what do we do? So this pole has a 0, right? First of all, before that, how many lock key do we have? 2, right? So the first one goes here, the second one, so you have a pole, the lock key has to start from the pole, right? You don't have a 0, what will happen? No. You know, like everybody has a soulmate. That soulmate is taken. It has to find his own soulmate. So it goes to infinity. And it's, yeah, it's going toward sunset. So goes to sunset. 2 lock keys. I like this part of it. Like the one that don't have a 0, great. You're just going, I don't need to know where you're going, you're going. Now, there would be different ways of, like, it's not always underline straight, right? There are different ways, but those are other rules. But for now, one simple way is that going straight to find a 0. Yes.
Do they always go to the left?
So rule number 2 goes from pole to a 0, right? There are no 0. If it goes to the right side, it goes to unstable region, right? That's what we don't want. You want to send it to the stable region. So it goes to the stable. Now, sometimes it doesn't always go flat like that with 180-degree angle. Sometimes there's an angle. There's a rule for that. How do we know? There's even a rule why this is 180. We say 180 because you measure the angle from the imaginary line. So there are other rules for it. But yeah, this guy is going to infinity. How about this case? How many lock keys? 2. 1 from pole to the 0. There is a 0 without a pole. What's happening? Where is the soulmate? In the infinity. The soulmate is coming from infinity. Just use this analogy. It works 100% of the time. It comes from infinity and gets there. Now, we have a way of calculating the angle so you make sure it's on a straight line, but it's going to be from the infinity. So we're assuming it's in a very, very harder place that we don't know. Okay. Good, the first 2 rules. So we either the number of equal, super easy, or the numbers one is less than the other, then you assume they're in the infinity, they're coming. So that's the first 2 rules, super easy. Rule number 3, if the roots are complex, like the example we had 3 plus minus 1j, they mirror each other. So they move together. So whatever the first one, like if there was a pole, like a conjugated pole, there are gonna be conjugated zeros that they go to. If not, they will go to infinity, both of them. So there's literally a mirror and then they behave that way. All right. Rule number 4, at no time will the same root cross over its own path. So there's no wiggly lines. There's always a straight, like when I say straight, it could be curved, but they could not be like flowery kind of things. So let's check that out. So let's check root number 4 because it's super easy. Then I will check number 3, some example for that. So let's say this was your pole to 0. This never happens. As you saw in the previous page, it goes on a straight line. It does not cross over itself. Okay. And this guy is in infinity. There. Now, rule number 3, let's work on an example. Let's say, let's give you some unstable system. How many locus you're gonna have? 3, right? So we have a pole, we have a 0. From pole to 0, well, the system is unstable. We're gonna fix that. Now we have 2 poles without soulmate. They're conjugated. What should happen here? They go to infinity together, but 2 different infinities because one is not going after the other soulmate, right? So this one goes, finds the soulmate. This one's like goes to North Canada. The other one goes to Alabama. They're both happily ever after, but we know their direction. They go together, all right? Whenever it's too much, you can tell me. I just enjoy this too much. Yes. They're not going to imaginary. Oh, you mean they're going up, not going straight? There isn't a rule for that. They would leave with 90-degree angle. So there are 8 rules. Once you know all of them, this makes sense. So those are hard, like a little bit harder rules because you have to calculate things. So I put them at the end. So I'm dragging you into this, like this is fun. No. So those rules comes up. Don't worry about it. So this is basically that. That's why. Asking good questions, though, I like it. These are very good questions. All right, let's see rule. So that's rule number 4. Okay, let's give you another example. We actually just saw this before. You saw this before, right? How are the root locus? Now here, if you don't have the knowledge of the previous, of the next, the rules after here, you all can draw different things. You just know that there are 2 poles and they're not conjugated because they don't have imaginary part, right? But they don't have 0, so they don't have to go to infinity. But you can draw the infinity in many different ways, correct? So you would need a little bit more information, which are the next rules. But as we saw before, one went that way, the other went this way, all right? So you see that these 2 are moving along an asymptote, right? The line that both are going toward and then both of them. So that asymptote is something we're gonna find. And then you would know if there is an asymptote and we will have the angle of that asymptote, we know the root locus has to go by it. There's only one way to do. So basically, calculate a few things and what are the possible ways for root locus to go? That's one thing. The other way, draw all the K. So plug all the K, find all the poles, and then do that. Yeah.
It's always going to be relaxed.
It is going to be always not vertical, yeah. Going to cross the
But it's always
Real
on
axis.
the real axis or the deviated, so like it's on the real axis.
That's the imaginary axis.
Oh, sorry.
No, it is going to be vertical to the real axis, but can move. So your asymptotes
Yeah.
would, well, not always,
Like,
but there will be an angle for that asymptote.
okay,
They also can be like that. But they are, I don't remember if they are parallel. But you don't need to worry about it because you will calculate the angle of the asymptote. Then you draw it. So you draw the asymptote and then you basically are checking, okay, I found this, there are 8 rules that I can place, and then what are the possible ways for root locus to go through? There are some very complex example that you would not know until you actually draw a couple of Ks, find the roots and then poles and then draw that. So we won't, that's why I decided to just use MATLAB, because for those complicated ones, why do we suffer just draw with MATLAB? Yeah.
so for those root locus, because the one pole goes down, that's because we calculated 0 degrees right of
No. So this will be, you had the asymptote. The only way is that it has to go by asymptote. If there is an asymptote, the poles have to go by asymptote. So it will be next rule. So from the first 4 rules, all you know is there's going to be 2 locking, and it has to go from the 0, from the pole to a 0. Now, since you don't have a 0, it is an infinity. So you could actually draw this if you didn't know. You would say, why not that? And I would say, sure, from the first rule, you're good. I'm just showing you what actually looks like, so it means that there's more to it. All right, so let's get to it. Rule 5, locus lies on the left of the odd number of pole and 0. So nobody asked me here, why didn't you do this? You know, why did I not? I'm gonna draw with this guy. Why did I not draw this or that, or I don't know. At least this first one makes sense, right? It could have been from the pole to 0. But since nobody asked, there's a rule for it. You can't do it. The rule is that the lines, the lockies, who's talking? You're really distracting me. The lockies will always be placed on the left of the odd number of pole and 0. Now, the pole itself should not be even or odd, like 2, 1, 3, the number of them. So if you have 3 poles, 1, 2, 3, 1, 2, 3, this is the odd, this is the odd. So we know that the locky would be on this side of this, the left of the odd number. So if there's a 0, you connect to it. If not, has to go to infinity. All right. So there could be cases there is no 0, so there's gonna be asymptotes, and they're gonna be like that. They will go to infinity. All right. So this is another piece of information you have. Rule number 6: lines leave, break away, or arrive on the real axis with 90 degrees. So whenever they are coming to the real axis, is going to be 90. All right. So if we calculate an asymptote like that, let's say there were 2 zeros, this would have to come like that. Does that make sense? And this one had to come because it has to be close to 90 when it gets to the line. Now, if there was no asymptote, then they would have to, for example, go across in 90 degrees here. Either it's close to 90 if there was an asymptote, or if it had to cross, it had to be 90 degrees. All right. So we call those breakaway point or takeoff point. Break-in. Break-in is when the pole is in infinity or somewhere further. Breakaway is when your pole is on the real axis and you're taking away going to infinity. All right. Rule number 7, if there are not enough polar zeros to make a pair, the extra line goes or comes from infinity. We already talked about that, right? All right. Let's check this example that we already solved. So if there are two poles here, they're both on the real axes, all right? Let me make this a 0 so it's a lot simpler. So this is first, this is second. The second pole or 0, okay? Then the loci starts from a pole and it will be on the left side of the pole. So this is the left side of this pole. So this is the right side. So it's going to be on the left side. Another example, let's do this. This is more, has more pole and zeros. And I let you do that by yourself, and then I will solve it myself. How many loci? All right, then let's see if we can draw something. Try to guess. It's okay. Based on all the rules you know so far. So I'm gonna just help you with this. Is the first one, second one, third one, fourth one, fifth one. So this, from this pole, where does this go? It has to go from a pole to 0, right? So I know the 0 is the receiving part. So it has to go from this pole. Now, should it go to the right side now or left side? It's to the left of the odd number of poles or zeros. Which one the odd number? First, which is the pole, the 0 here. So this is the left of it, right? But the direction would be, so the loci will be placed on the left side. Okay, just the line, but we know from the rule number 2 that is always from pole to 0. Why does it matter? That is from pole to 0. Like, why the direction matters? What does it imply? So you're changing k from 0 to infinity, right? So this means that this k is less than this k. To give you a better idea, if you wanted to place, like you put 1k and then it's like, oh no, too close. What's your next guess? Okay, looks like it has to be the greater. Oh, you're out of time. Okay, so I'm gonna just show this. You cannot do class participation. Good for you. Although I want you to do it. So this has to be 2/3 here and then here, but this is not possible. So you would know this would be something like that. That is rule number 8, which I didn't tell you because it's the harder one. Now, for class participation, you cannot do the centroid and asymptote. You can do the first 2, I think. So based on the first 7 rules, answer the question, and then I ask you to plot the root locus using MATLAB. Just rlog, I gave you the command, put the system in it, and see how it looks like. And then on Monday, I will give you rule 8, and then you will draw that. Okay. Passcode is, hold on. Yeah,